Right outside the front door is this gigantic picture of this Indian god that is standing inside of a portal.
Deep underground, a massive ring-shaped machine known as the Large Hadron Collider, LHC, smashes particles together at astonishing speeds. This groundbreaking device, located at CERN, is at the forefront of scientific discovery, pushing the boundaries of our understanding of the universe. However, some fear that these experiments might have unintended consequences.
That is standing inside of a portal, walking through. So I think they kind of knew what they were going to be doing when they started this whole building.
Could the scientists at CERN accidentally open a portal to other dimensions, unleashing demons and turning Earth into a living hell? Join us as we explore the terrifying possibilities of these high-stakes experiments and the potential for a devastating shortcut to chaos, pushing the boundaries of particle physics. The Large Hadron Collider, hiding beneath the Earth near Geneva, is a scientific marvel, much like something out of a sci-fi movie. This huge ring, stretching 17 miles across, lies buried up to 574 feet underground. It's not just any machine. It's the biggest and most powerful particle smasher in the world. Deep underground, in this massive tunnel, the LHC operates at mind-boggling extremes. Using super-cold superconducting magnets, colder than outer space at minus 456.34 degrees Fahrenheit, it speeds up particles to near the speed of light. These particles zoom around the tunnel, racing in opposite directions before smashing into each other at 4 key spots equipped with giant detectors. This setup is designed to mimic the conditions just moments after the universe began, offering clues about the fundamental nature of everything. The LHC is more than just a particle crash site. It's a complex of accelerators, each one building up the particle's speed and energy before passing them on to the next, until they're whizzing around at incredible speeds. One of these steps, the superproton synchrotron, itself a giant at almost 4.3 miles around, shows the scale of this massive scientific endeavor. These experiments conducted at the LHC are critical. They test theories that are central to our understanding of the universe. From confirming the existence of the Higgs boson, which helps explain why particles have mass, to hunting for evidence of dark matter and exploring why there's more matter than antimatter in the universe. Each discovery or piece of evidence gathered could open new doors in science, potentially leading to new technologies or revisions of our fundamental theories. Yet, those who question have a valid point. How far are the researchers willing to push in their quest for knowledge? The fears of accidental disasters are not just unfounded worries. They are based on genuine concerns about tampering with the fundamental aspects of nature. And while the public story focuses on scientific exploration, some people wonder if there might be other goals that are not being shared, which could step into areas of questionable ethics. CERN is a major center for science, where researchers are trying to connect the wonders of science with teachings from the Bible. They hope that by combining these two areas, people will follow religious teachings more closely. Meanwhile, the history of mathematics is a long one, stretching from ancient civilizations to today, mostly focusing on practical uses rather than just learning for the sake of learning. In ancient Greece, across the Mediterranean, mathematics was also mainly practical. Famous people like Pythagoras, Euclid, and Archimedes are known not just for their ideas, but how those ideas were used. Pythagoras' theorem, which we now see as a basic part of geometry, was first used for measuring land. Euclid's Elements, a key book in geometry, was written not just to explore ideas, but to help with practical things like planning cities and building structures. Archimedes is praised for his early ideas about calculus and important work in geometry. However, he was also focused on solving real problems of his time. He came up with inventions and theories out of necessity, whether it was building war machines to protect Syracuse or creating devices like the Archimedes screw to move water. As centuries turned, the application of mathematics mirrored the immediate needs and challenges of societies, evolving from basic counting systems to more sophisticated theories and models that underpin modern science and technology. The continuous refinement of mathematical tools and theories was driven by real-world issues, from constructing ancient megastructures to solving contemporary engineering challenges. This long of mathematics, often seen as a noble quest for truth, has been fundamentally of survival and practicality. Each step in the evolution of mathematics has been a response to societal needs, from the architectural marvels of ancient Egypt to the complex data models that guide today's technological innovations. The unfolding saga of mathematics, each period marks a distinct chapter in the relentless pursuit of knowledge. The narrative begins in the ancient era, where the basic principles of mathematics were established. These principles laid the groundwork for all mathematical thought that would follow, forming a robust foundation that would support centuries of intellectual exploration. As the timeline progressed into the classical period during the medieval times, the Islamic world emerged as a powerhouse of mathematical development. Scholars in this region were not merely content with preserving the wisdom of ancient Greeks, they sought to enhance it. Among these scholars, Al-Khwarizmi stood out. Known as the father of algebra, he expanded the boundaries of mathematical thought, introducing the concept of algorithms, a term inspired by his own name. This era was characterized by a vibrant exchange of ideas, making it a crucial period for mathematical advancement. With the dawn of the Renaissance in Europe, there was a renewed interest in the mathematical sciences. Figures such as Leonardo da Vinci and Johannes Kepler delved into the complexities of geometry and the nascent field of calculus. Their efforts were not merely about rediscovery, but about pushing the envelope of what could be understood and achieved through mathematical inquiry. Following this resurgence, the Age of Enlightenment brought about a transformative period in mathematics. The 17th and 18th centuries were defined by the development of calculus. Isaac Newton and Gottfried Wilhelm Leibniz, working independently, formulated new approaches to understanding change and motion, setting the stage for future advancements in multiple scientific disciplines, including physics and engineering. Next, we explore how early math wizards set the stage for today's technology. The Pythagorean Code of Silence. The 19th century continued to see mathematics evolve with the establishment of structures like mathematical logic and abstract algebra. Pioneers such as George Boole, Augustus de Morgan, and Évariste Galois further developed these ideas, which would later form the backbone of modern mathematical thought. Meanwhile, the exploration of non-Euclidean geometries by Carl Friedrich Gauss and others began to challenge conventional notions of space, paving the way for revolutionary theories, such as Einstein's theory of relativity. The narrative enters the 20th and 21st centuries, a time of unprecedented growth in mathematical theory and application. This era saw the emergence of set theory, topology, and number theory, propelled by the minds of brilliant thinkers like Kurt Gödel, whose incompleteness theorems questioned the very limits of mathematical proof. Alan Turing's work on computability laid the groundwork for modern computing, while Andrew Wiles' proof of Fermat's last theorem solved a centuries-old problem. Members of the Pythagorean Brotherhood followed strict lifestyles, engaging in practices such as sacrificing animals and avoiding discussing religious matters. They also abstained from sexual activities and even from touching beans, which is an unusual prohibition. They held the pentagram, a five-pointed star, in high regard, believing it had special powers and was central to their beliefs. This admiration for a geometric shape as a powerful symbol should cause concern for those who value rational thought. Turning to a later historical figure, Isaac Newton, another well-known name in the realms of mathematics and natural philosophy, also had his quirks. Born on January 4, 1643, in Woolsthorpe, Lincolnshire, England, he attended the University of Cambridge. During his time at Cambridge, Newton developed a strong interest in alchemy and the esoteric teachings of the Hermetic tradition. Alchemy, which is the ancient pursuit of turning ordinary metals into gold and discovering the philosopher's stone, captivated him throughout his life, leading him to conduct numerous experiments and write detailed notes on his findings. Newton's alchemical pursuits were deeply intertwined with his scientific research. With his alchemical manuscripts, full of detailed notes and diagrams, only becoming public in the 20th century. These writings reveal a man deeply committed to uncovering what he saw as profound truths about the natural world, influenced by ancient and mystical thought. This combination of Enlightenment science and mystical interests portrays Newton as a man balancing on the edge between groundbreaking insight and unconventional beliefs. Hermeticism in ancient Greece focused keenly on the pursuit of spiritual knowledge and adhered to the belief in a cosmic order governed by divine principles. Among its modern adherents was Isaac Newton, whose profound interest in these ancient doctrines was evident. He meticulously annotated Hermetic texts and incorporated Hermetic symbols into his alchemical research. This deep engagement raises little surprise that Newton, during his academic tenure at Cambridge, became affiliated with the Masonic Lodge. This connection was often discussed, especially in terms of its influence on NASA and Aleister Crowley, the founder of the Ordo Templi Orientis Society, deeply rooted in occult and Hermetic practices. The society, inspired by Newton's theoretical work, played a pivotal role in developing the rocket technology foundational to NASA, an organization named to honor Newton's legacy. The Masonic Lodge at Cambridge, known as the Isaac Newton University Lodge, was established in 1861 under the auspices of the United Grand Lodge of England. It was crafted specifically for the academic community at Cambridge, welcoming students, faculty, and alumni to participate in its Masonic rituals and traditions, maintaining a continuity of intellectual and esoteric pursuits among the academia. Shifting focus to another monumental figure in the sciences, Albert Einstein, whose life and work echoed through the corridors of modern science, was inherently connected to the Enlightenment's progressive ideas, yet firmly planted in the modern era. Born on March 14, 1879, in the small city of Ulm in the Kingdom of Württemberg, part of the German Empire, his family moved to Munich shortly after his birth. Einstein's early years in Munich were marked by an acute curiosity in mathematics and science. Self-educated in advanced theories of math and physics, he later enrolled in the Swiss Federal Polytechnic School in Zurich in 1896 to further his studies in these fields. Despite his unconventional methods and occasional confrontations with authority figures, Einstein's academic performance was stellar, culminating in his graduation with a teaching diploma in 1900. Now, we dive into a century of big ideas that changed how we see the world. The dawn of modern physics. Einstein had a tough time finding a steady job in the academic world, so he took various teaching gigs and worked at a patent office. But in 1905, he had a breakout year, known as his miracle year. During this time, he published 4 groundbreaking papers. His first paper introduced the special theory of relativity. This big idea changed how people thought about space and time, showing that the rules of physics are the same for everyone moving steadily, and that light always travels at the same speed in space. His next major paper gave the world the famous equation E is equals to mc squared, which shows that mass and energy can change into each other. This concept totally changed the basics of physics and how we understand the universe. At 1240, this insight was key to developing nuclear energy and hugely influenced modern physics. By 1246, in his work on how tiny particles move unpredictably in liquids, Einstein backed the idea that everything is made of atoms, providing solid proof they exist. Going on to 1304, in his study on how light knocks electrons off metals, he proposed that light is made up of particles called photons, not just waves. This idea won him the Nobel Prize in Physics in 1921. Even though Einstein focused on physics, by 1318, he showed some interest in bigger, philosophical questions, though he didn't dive into spiritualism like some of his peers. By 1332, he mentioned that if someone doesn't follow Christ's teachings, their supposed inner light is actually darkness, an odd way to mix personal beliefs and science. By 1345, discussing his views on quantum mechanics, Einstein didn't like the theory's reliance on randomness. He famously said, "God does not play dice with the universe." preferring clearer, predictable explanations. This showed he might believe in a more orderly, possibly divinely organized universe. By 1421, interpreting Einstein's philosophical thoughts can vary. He seemed to balance solid scientific ideas with thinking about a grander universe, possibly guided by some divine force. This mix makes him a complex figure in science, respected yet continuously explored for how his scientific work might suggest broader, more profound themes. His legacy still sparks debates about the mix of science and deeper ideas, showing how even a dedicated scientist can explore big, overarching themes. Einstein admired the thoughts of Baruch Spinoza, a thinker who believed that God and nature were one and the same. When talking about his own beliefs, Einstein mentioned feeling a deep respect for the universe's splendor, which some might interpret as having spiritual undertones, though he never confirmed any direct connection to mystical ideas. There's ongoing speculation that new documents might eventually surface, revealing more about Einstein's sources of inspiration, much like the surprising finds related to Isaac Newton in the past. People often say that the true nature of something is shown by what it produces. In Einstein's case, his discoveries, while revolutionary, also brought us closer to potential devastation, highlighted by his role in developing nuclear technology during the Manhattan Project. Looking at the broader context of history, it's important to examine the forces that fueled the rapid advancements during the Industrial Revolution. This era was marked by significant leaps in areas like mathematics and science, where Einstein would later make his mark. What sparked this era of rapid development? Moreover, who or what was the hidden force behind these changes? In his presentation, he outlines a sequence of events involving the Nephilim, Nimrod, NASA, and theories about the Earth being flat. He connects the release of ancient fallen angels to a rapid increase in human technology and knowledge. His theory suggests that by the early 1960s, just a few years after the first simple satellite, Sputnik, was sent into space, we were already sending probes to Venus and Mars. This was before we even landed on the Moon in 1969. It's difficult to believe that in just a few years, our technology went from basic satellites to complex space missions. Moving on, let's see how ancient stories and modern science start to merge. Technologies leap in the shadow of war. He points out the distances to these celestial bodies, emphasizing the improbability of such early interplanetary missions. The Moon itself is about 240,000 miles away from Earth, and Venus and Mars are even further. Yet he claims that in the early 60s, probes were allegedly heading toward these distant planets before any human had walked on the Moon. He references official mission logs from a space agency's website, which apparently show that immediately following secretive operations in Antarctica, both the US and Russia began sending missions to Venus and Mars, along with conducting high-altitude nuclear tests. He argues that these actions might seem to support those who believe in elaborate theories involving government secrecy. Additionally, he introduces the idea of ancient gods returning to Earth. He refers to the Book of Enoch, which mentions that these celestial beings, known as the Watchers, were locked away for 70 generations. He uses Psalm 90 to define the length of a generation to support his claims. According to him, the preparations for the return of these beings have been meticulously arranged. Despite his detailed connections and historical references, the entire discussion feels more like a mix of elaborate fiction than a plausible account. The blending of ancient texts with events from the Cold War era results in a narrative that is complex and hard to follow. It's as if he's assembling a complex story from different pieces of history and mythology, presenting it as a coherent plot. He does so earnestly, suggesting a picture only he fully understands. Imagine a timeline stretching back 4,900 years from the start of the 20th century to 3000 BC, a period marked by the judgment and confinement of the so-called Watchers. As the 20th century dawned, there was a remarkable shift from the slow pace of horse-drawn carriages to the rapid emergence of technology. These included airplanes, trains, automobiles, computers, and even missions that reached the Moon and the farthest expanses of space. This sudden burst of innovation within a mere 50-year span raises the question: was it merely a coincidence, or was there an unseen influence accelerating these advancements? During this period, the world experienced the devastating impact of two global conflicts that claimed millions of lives. Some theories suggest that such massive bloodshed could fuel otherworldly entities that supposedly feed on human sacrifices. This idea posits that the chaos of war might have indirectly powered the dramatic technological leaps observed during the 20th century. Historical records show periodic spikes in human knowledge and capability. The biblical book of Daniel, for instance, refers to a time when knowledge would increase. However, following the event at the Tower of Babel, where a multitude of languages was suddenly born, the collective intellectual progress faced a severe setback. Brilliant minds, once united, found themselves isolated by language barriers, drastically slowing the pace of shared innovation. Those fortunate enough to collaborate with minds like Nikola Tesla might have managed to continue making strides, but many were left to struggle with lesser talents. According to some beliefs, this fragmentation of human knowledge was a divine act intended to scatter and humble an overly ambitious mankind. Consequently, intellectual and technological advancements stagnated for centuries, only to surge unexpectedly at the onset of the 20th century. The midst of these dramatic shifts, Albert Einstein emerged as a key figure in the scientific community. His indirect connection to the Manhattan Project, which aimed to develop the atomic bomb during World War II, was more symbolic than practical. Despite his minimal involvement, Einstein's theories laid the groundwork for the project, and his reputation helped to enhance its significance. His association with the project, though largely honorary, linked him indelibly to this monumental effort in the public memory, overshadowing the nuanced reality of his actual contributions. Einstein was crucial in initiating the United States atomic research during a tense pre-war period in 1939. He collaborated with physicist Leo Szilard to write a critical letter to President Franklin D. Roosevelt. This letter wasn't just a routine correspondence. It urgently highlighted the destructive power of atomic energy and its potential use in weapons. The communication emphasized the need for the U.S. to advance its research into nuclear fission to prevent Nazi Germany from gaining a lead in this new technology. Reacting to the letter's implications, Roosevelt swiftly established an advisory committee on uranium. This committee was the precursor to what would later expand into the Manhattan Project. Now, we step into a time when bold experiments unlocked the power of atoms. The minds mastering the atom. Albert Einstein played a crucial role in the development of nuclear technology, though he was never directly involved in the day-to-day operations of the project. His early warnings about the power and dangers of nuclear energy laid the foundation for a major shift in modern warfare and global relations. Despite his foundational contributions to nuclear theory, Einstein acted more as an advisor than an active participant in the project. He helped initiate the project, but didn't influence its ongoing execution, staying more in the background of the monumental task he had helped to start. Einstein's support was critical in motivating the U.S. government and the scientific community to invest heavily in the Manhattan Project. His endorsement brought necessary attention and credibility to this complex scientific effort. The Manhattan Project was a groundbreaking scientific initiative, gathering some of the brightest minds of the time, such as Niels Bohr and J. Robert Oppenheimer. These physicists faced the enormous task of translating theoretical physics into practical applications. Their main goal was to harness nuclear fission, relying on advanced mathematics to do so. Quantum mechanics, a field developed in the early 20th century, provided the mathematical basis to understand particle behavior at atomic and subatomic levels. The Schrödinger and Dirac equations were essential for modeling electron interactions and other particle dynamics within atomic nuclei. In Chicago, Enrico Fermi led another crucial project at the University of Chicago, focusing on creating the world's first nuclear reactor, Chicago Pile 1. Fermi's deep understanding of mathematics helped him design the reactor core and predict its behavior under different scenarios. His work was a practical application of physics with immediate significant impacts. The Manhattan Project was a hub of intense scientific effort where theoretical concepts were put to practical use. The collaborative work of physicists, chemists, and engineers expanded the boundaries of scientific possibility. Each calculation and experiment aimed to deepen understanding of the universe's fundamental forces. Einstein, though not involved in the day-to-day efforts, continued to support and advocate for the project, reinforcing its importance and the potential significance of their findings. This project was centered on building an atomic bomb, demanding a thorough grasp of intricate nuclear physics. A key focus was managing neutron movements and multiplication in nuclear reactors, using equations and models crucial for controlling nuclear chain reactions, essential for power generation and bombs. Enriching uranium-235, necessary for the atomic bomb, was a significant challenge. At Columbia University's Kellogg Laboratory, directed by Harold Urey, scientists developed a gaseous diffusion method using gas dynamics and statistical mechanics principles to separate lighter uranium-235 from heavier isotopes. Another major task was designing the bomb at the Los Alamos Laboratory. Physicist Seth Nettermeyer devised a method using conventional explosives to compress a smaller, safer uranium amount until it reached a supercritical state, sustaining a chain reaction. Understanding shockwave behaviors and material responses under high pressure was critical to perfecting the explosion's timing and shape. Stanislaw Ulam and John von Neumann were towering figures in the fields of mathematics and physics, and their groundbreaking work significantly advanced the development of nuclear weapons and computational methods. Their contributions are essential to understanding the scientific strides made in the mid-20th century, particularly during and after World War II. Born in what was then Austria-Hungary, Stanislaw Ulam was a gifted mathematician from his early years. His path in academia took him across Europe before he finally settled in the United States. It was here that he joined the Manhattan Project, a U.S. government research project aiming to develop the first nuclear weapons. Ulam's work at Los Alamos, the project's central laboratory, was crucial. He contributed to the development of the hydrogen bomb by improving the design of the implosion mechanism necessary for detonating these powerful weapons. However, Ulam's most famous contribution came in the form of the Monte Carlo method. This revolutionary approach uses randomness to solve problems that might be deterministic in principle but are too complex for straightforward analytical solutions. This method was co-developed with John von Neumann and has since been used in various scientific fields, influencing everything from economics to quantum physics. John von Neumann, born in Budapest, Hungary, was recognized as a prodigy early on, displaying an astonishing aptitude for languages and mathematics. His contributions span multiple disciplines, including quantum mechanics, functional analysis, economics, computer science, statistics, and more. During World War II, von Neumann's skills were put to use in the Manhattan Project alongside Ulam. His work on the calculations for nuclear fission helped ensure the success of the project. Von Neumann was instrumental in developing the mathematical models that described the behavior of nuclear explosions. After the war, he continued to influence the development of computer science, particularly through his work on the architecture of digital computers, which laid the groundwork for the systems we use today. Ulam and von Neumann's collaboration at Los Alamos was not just about building bombs, but also about laying the foundations for modern computational techniques. Their development of the Monte Carlo method was particularly significant. This technique uses random sampling to approximate mathematical calculations that are too complicated to solve directly. Over the years, this method has become a cornerstone of statistical simulation, aiding in everything from weather prediction to economic models. Beyond their technical achievements, both men were deeply involved in the philosophical and ethical implications of their work. They were among the first to consider the long-term impact of nuclear weapons, advocating for both scientific advancement and caution in the use of new technologies. What do you think about the ethical implications of using such powerful technology for warfare? Like, comment, and subscribe to join the discussion and stay updated on more content.